In this video, we discuss OpenGL gluLooAt and model view transformation. In the previous video, we have discussed OpenGL perspective projection, which is defined by the command gl_fustom with parameters LR, BT, and F, representing left, right, bottom, top, near, and far. This defines a viewing volume, viewing fustom, as shown in this figure. In this figure, O is the origin and the I position is located at this origin and is looking in the negative C direction. All scenes inside the fustom are projected onto the near plane. In practice, we can define our own I position or viewpoint and orientation of the fustom. Then we use model view transformation to have to move the viewpoint to the origin and the visible objects into the fustom. The function gluLooAt provides these features. Acknowledgements. Most information presented here is obtained from this book by Fortune. Now, this is as a demo about the concept that we just discussed. So this is the fustom, and this is the camera up vector, and so from here we are looking at this object, and gluLooAt will move this origin, the I position, to the coordinate origin and rotate the axis, so the object will be aligned with the y-axis, and the line of sight will be along the negative z-axis. So that's what happens. So first you move everything, the I position to origin, and then it does a rotation that will rotate the object into the fustom, and the up vector is aligned with the y-axis, and the I is looking at the negative z-axis. Now here's the specification of gluLooAt. So yeah, these are the parameters. Ix, Iy, Iz specifies the position of the I point. Target X, target Y, target C specifies the position of the I is looking at. And up X, up Y, up C specifies the up vector. gluLooAt creates a viewing matrix derived from the I point, the target point, and the up vector. So basically, we have three quantities: I, target, and up. And these have been shown in the demo. Now the confusing part is the up vector. The up vector should be perpendicular to the line of sight, as shown in this figure. So when we aim our camera at this direction, this is the line of sight, and this is our up vector. When we aim the camera at a target, the line of sight is defined. We only have the freedom of rotating the camera, which orientation determines the up vector. However, we cannot tilt the camera, otherwise the target will be changed. gluLooAt allows us to define any up vector pointing in any direction as long as it is not parallel to the line of sight, apparently in contradiction with our understanding of the up vector. The trick is that the function figures out the plane formed from the line of sight and the up vector we provide. Then if we calculate the up vector so that it is perpendicular to the line of sight. Thus in this figure, the I and the target forms the line of sight, and we have 3 up vectors, up 1, up 2, up 3. They are all in the same plane, so they will have the same effect, producing the same model view transformation matrix. Say, for example, gluLookAt with this I position, this target, and up vector 0, 1, 0, and the other with the same I, same target, but a different up vector still in the same plane. Then they will produce the same model view matrix because up vectors and the line of sight are all in the same plane. But, let me demonstrate this to you. So in this program, we have 2 arrays, P1, P2, and so this defines the projection matrix, and then we switch to model view, no identity. So we consider this gluLookAt with up vector 0, 1, 0, and we save the matrix in P1, and then we try again. Start with identity matrix and try this gluLookAt with same I and target, but different up 8, 9 is 0 in the same plane as this. And we save the model view matrix in P2. So we print out P1 and P2 and see whether they are the same. So we can compile this. And now you can see that the matrices printed out using the 2 different gluLookAt are the same, meaning that even though the up vectors are different, but the effects are the same. So in the following shows how gluLookAt effectively calculates the transformation matrix. The actual implementation could be different from the presentation here. First, it moves the I position to the origin, which is done by the translation matrix, as it has been shown in the demo. So this is TE, negative IX, negative IY, negative IZ. This translation will move the I to the origin. All objects and points will be translated by this matrix. The target will become target dash with components target X dash, target Y dash, target Z dash, which is equal to target X minus IX, target X minus target Y minus IY, and so on. Everything is shifted by I. The up vector is still the same, as a vector won't be affected by translation. Second, it finds an orthonormal coordinate system centered at the I position, which is now at the origin, and defined by the line of sight and the up vector. This is done in the following way. First, we calculate a forward vector from the target to the I. F equals origin O minus target dash, that is negative X dash, target X dash, and so on. And then we normalize that. The negative F is the line of sight. So later we have to rotate F into the Z-axis. The negative Z-axis will be the line of sight. Second, we calculate a right vector perpendicular to F using this cross product. Right is equal to up cross F. Okay, up is provided by us. Okay, and we normalize it. Say R is equal to right divided by its magnitude. Okay, so both F and R are unit vectors perpendicular to each other. Okay, but we calculate up to form an orthonormal basis. So U is equal to F cos R. Okay. From the unit vectors R, U, and F, we form an orthonormal basis. Okay. We want to find the transformation matrix that brings R into X, that's 1, 0, 0, U to Y, 0, 1, 0, F to Z, 0, 0, 1. Okay. It is obvious that the matrix that transforms X, Y, Z to R, U, F is given by this matrix. Okay. Rx, Ux, Fx, and Ry, Uy, Fi, so on. For example, say with the R, okay, at the point R, Rx, Ry, Rc1 is equal to say this times the point 1, 0, 0, 1. Okay, so 1 times Rx gives us Rx, Ry times 1 gives us Ry, Rc times 1 gives Ry, all others are zeros. Okay. The rotation matrix, say Trx, that brings Ruf to xyz is the inverse of Txr, the inverse of this. Okay. Or Trx is equal to Txr inverse. Okay. However, Txr, this matrix, is an orthogonal matrix as each column vector has a unit length and the dot product of any two column vectors is equal to 0. Like the dot product of this column and this column is basically R dot U. It is equal to 0. Okay, so it is orthogonal. And we know that an orthogonal matrix is inverse is equal to its transpose. Therefore, Trx is equal to the inverse of Txr equals Txr transpose. Okay, so it is given by this. That means we interchange the row and the column. Okay. So the model view transformation matrix that brings the I to the origin and analyze we calculate up vector with the y-axis and align the line of sight with the negative z-axis is given by this TMV equals Txr times Te, okay, or the product of these two matrices. Okay. Now I can demonstrate this to you using a program. This is the program that we'll use. Before that, we have some utilities for vectors. So in this utility, with some functions, a cross product that calculates the cross product. C is equal to A cos B, very straightforward. Dot product, okay, and normalize a vector, add two vectors, okay, and minus vector is to calculate the difference between two vectors, okay, and the first argument is always the output. Okay. Copy and so on, and the transpose. this is the program for demo, nothing special. Now, this is the array that defines the I, okay, 646, the target 323, the up vector 898, okay, and these are the forward, right, up vectors, okay, that we just discussed. And R is the rotation matrix, okay, that rotates the FRU so that aligns with the XYZ, okay, RUF, okay. And RT is the transpose of R. Okay. P1, P2 are two arrays, two-dimensional arrays to save the matrices. Okay. First, we define the projection matrix, okay. And now we consider a model view matrix. Okay, we start with identity. So this is the gluLookAt with I, target, and up. Okay, we put this matrix into P1. Okay, and then now we try again. We start with identity matrix, and we calculate the forward vector. Okay, I minus target minus vector, and normalize it. We calculate the cross product up cross F to give us R. We normalize R, the right vector, and also we calculate the up vector U is equal to F cross R. Okay, and then we fill in the rotation matrix that we just discussed. Okay, and now OpenGL is column major, so we need to make a transpose. Okay. And then we multiply this to the identity matrix, okay, the RT to identity matrix, and then this followed by the translate. So actually we do the translate first, and then the multiply, and then all this will be multiplied together, okay, because translate is on the right side, it's nearer to the object. Okay. And then we put this, okay, into P2. So we want to compare P2 and P1. Okay. So P1 is the matrix from gluLookAt, and P2 is the matrix we calculate. Okay. That's not important. And so we compile it and execute this. Okay. And now you can see that the matrix from gluLookAt is the same as the transformation matrix we calculated based on our discussion. Okay, they're identical. So that means gluLookAt indeed works in the way we described. Now at the end, a point is transformed in this way. First, it is transformed by the model view matrix, and then by the projection matrix. So P here is the projection matrix, TMV is the model view transformation matrix. And actually, we may treat the projection matrix as a model view matrix. So in this sense, in this case, we have the projection matrix loaded into the projection matrix P. Okay. And we have the model view matrix loaded into the model view matrix. And at the end, they will be combined. So this actually is the same as this. The projection matrix is simply identity. Okay, and then we change to GL model view mode, and so this projection matrix is loaded into the model view matrix and multiplied to the view matrix defined by gluLookAt. So they will have the same effect. I can show this to you. And let's see. So this is what we see, right, by the normal projection matrix. And suppose we change this. So we move the GL first term here. So the projection matrix is just identity matrix. And move this to here, for example. Okay. Then you'll see the same thing. So this is loaded into the model view matrix, or multiplied to the model view matrix, which is identity. We compile this. So you can see that we still see the same thing. Okay. So this shows that the two cases are equivalent. Okay. Okay. So you can go through this again by yourself, okay, and try to understand all these. Okay. Okay. Yeah. Thank you for watching. Okay. Bye.